So for the next few talks, we're going to be discussing where architectural form comes from. There are many, many sources of architectural form, but in particular for the next couple of talks, we're going to be looking at sources of architectural form in numbers, mathematics, and geometry, a really common source of architectural form. And then we'll have a couple of talks on organic, natural, biological sources of architectural form. So to begin this discussion of architectural form and its sources in numbers, mathematics, and geometry, I'd like to have a little talk about a very important figure in mathematics and someone who had a big influence in mathematics, in all kinds of things, and even in architectural form as well. This is a guy named Fibonacci. Fibonacci lived in Pisa in the 13th century primarily. And in 1202, Fibonacci published a book called Liber Abaci. And Liber Abaci introduced the idea of Hindu-Arabic numbers to the Western world. So prior to this time, Roman numerals would have been the numbering system that the entire Western world used. But obviously, Roman numerals have a little bit of a problem when it comes to computation. If you're trying to add XVIII and XII, this is awkward. It's a very cumbersome numerical system if you're going to try to do computation. So Fibonacci was one of the first people to realize that. And in Liber Abaci, he makes the argument for rejecting Roman numerals in favor of the Arabic system of numbers, which was much more computation-oriented. And he was interested in mathematics as not just a way of counting and accounting, but really as a way of solving problems and as a mode for understanding the way things work. So he's very interested in word problems. Now, you can imagine what a difference this made in the world. I mean, prior to this time, they're using Roman numerals. After this time, mathematics is a whole new tool, and there's a lot more possibilities. So this was a major, major contribution to the world of science and engineering and architecture and all kinds of things. But this interest that Fibonacci had in numbers was not just a practical interest. It also was a kind of intellectual interest and maybe even a spiritual interest in the way numbers worked. But first, let's look at what he did in terms of the way he thought of word problems or problems and the way you could solve them mathematically. So an example of a word problem that he was interested in, he said, let's say that you've got a pair of rabbits, and I'm interested in how they will breed to make X number of rabbits in a year's time. So the idea is you've got a male and female pair, and the rules he assumed were that every month that pair of rabbits could produce another pair of rabbits. But when a new pair of rabbits was born, it took a month for them to mature enough to produce another pair of rabbits. So he's saying, let's use mathematics to figure out how many rabbit pairs we'll have at the end of 12 months. So this produced these numbers. So in the first month, you have one pair of rabbits. In the second month, that pair of rabbits has one offspring. You have two pairs of rabbits. In the third month, the original pair can produce another pair, but the pair that was born in month 2 is still too young. So you really only have one additional pair, so that's 3 pairs in the third month. In the fourth month, you have the 2 that are now mature enough to produce an additional pair, and the 3 that existed before, and that gives you 5 in the 4th month. And then that continues on 8, 13, 21, 34, 55, 89, 144, 233. So that lets him use these Arabic numbers to figure out I'm going to have 233 pairs of rabbits at the end of 12 months. Now, that particular series of numbers, obviously we can generate it by just taking any 2 previous numbers, adding them together, and you get the 3rd number. Add 2 and 3, you get 5. Add 3 and 5, you get 8. Add 5 and 8, you get 13, and so on. And we can generate it ad infinitum. And that series of kind of seemingly random numbers is what's known as the Fibonacci series, in honor of Fibonacci, who figured this out. Now, that Fibonacci series, although you get it by adding, it also has an interesting relationship when you multiply and divide. So if you take any number in the Fibonacci series and you divide it by the next highest number, you get 0.618034. 0.618034. And it takes going a ways to get that precise number. I think after the 14th number in the sequence, you get exactly 0.618034. Now that's interesting because this, again, seemingly random series of numbers that you got by addition now has this multiplication division relationship between any 2 numbers. That number and that relationship of 0.618034 to 1 is what's known as the golden proportion or the golden section. It's also sometimes referred to as phi. And that was arrived at independently by the ratio A is to B as B is to A plus B. And so that's 0.618034 to 1 is equal to 1 over 1.618034. That again is a very interesting kind of numerical relationship that had been known for a long time and has been used over and over to produce what we call the golden proportion. This is the golden proportion. Now, you're reading Rasmussen's book, Experiencing Architecture. In his chapter on proportion, he has a fairly long discussion of the golden section or the golden proportion, and he derives it this way, as a ratio. But it also can be derived through the Fibonacci series. So now there's this kind of, wow, weird relationship between certain numbers and certain ratios that maybe have a special role. And people like Fibonacci were interested in exploring exactly what's that about. Now, that got to be very prominent in a number of different disciplines. This golden ratio has been used by musicians like Beethoven, Debussy, Mozart, Bartók in their compositions. Most Mozart sonatas are based on proportions that relate to the golden section. Beethoven's Fifth Symphony is based on proportions related to the golden section. People in science have looked at, as they're looking at the solar system, at various things in physics and in science, they have looked at the golden proportion and found it present in many elements of science. People like Pythagoras or Euclid or Kepler. Many artists have used it to proportion their paintings. The great German Renaissance artist Durer used it extensively. The Impressionist artist Seurat used it extensively. Michelangelo, both in his paintings and in his architecture, he used the golden proportion extensively as well. So there has been this history of a certain numerical relationship, a certain kind of magic that seems to happen between numbers in the Fibonacci series, certain ratios and proportions that have made these more prominent. Now, in the 19th century, there were these 2 German dudes. On the left is Gustav Fechner. Fechner is sometimes referred to as the father of psychology, very early psychologist. He was interested in some proportions psychologically being more satisfying to human beings than others. And so he looked around at all kinds of rectangles and books and notepads and windows and any kind of rectangles. And he was trying to see, is there some proportion of rectangle that seems particularly satisfying to people? Is that built into our psychology? And in fact, he found that the golden proportion, this 0.618034 to 1, or roughly it's easy to think of as 5 to 8, that proportion just was around him everywhere in German society. Then his disciple, a guy named Wilhelm Wundt, and this is a guy who was really now interested in, is there a physiological basis for some preferences like this? Do our minds, our brains actually have some built-in preference of this sort? And he started asking people. He did polling, and he was asking people which rectangles they preferred. And he'd have a whole range of rectangles. And he found that 75% of the people he polled preferred the golden section to other proportions of rectangles. So there was this interest in psychology of maybe something that's kind of built into our psyche that prefers certain proportions. Then this one just blows me away. So, there are two completely different systems of measuring distance. There's kilometers and there are miles, and they seemingly were developed completely independently. But then, oddly enough, if you're trying to make a conversion from kilometers to miles or vice versa, those ratios that we've been discussing and that Fibonacci series turn out to be exactly the relationship between kilometers and miles. So if you take that Fibonacci series and you take any two sequential numbers, the lower one will be miles and the larger one will be kilometers. So the Fibonacci series, remember, it's 1, 3, 5, 8, 13, 21, 34, 55. 5 miles equals 8 kilometers, two sequential numbers in the Fibonacci series. 21 miles equals 34 kilometers, two sequential numbers in the Fibonacci series. 55 miles equals 89 kilometers, two sequential numbers in the Fibonacci series. And in fact, if you're trying to convert, and I use this all the time when I'm in Europe and I see that sign that says how many kilometers, I think back to how close is that to a Fibonacci number, and you can rationalize if it's in between. But two sequential Fibonacci numbers will give you the comparison between miles and kilometers. Very handy thing, but weird. I mean, this number that is generated by addition, this number that also has this division, multiplication relationship, this number that can be generated by ratio and proportion, A is to B as B is to A plus B. It's embedded in our psyche and our preference visually for certain proportions. It's in these freaking measuring systems that were developed independently. There's something kind of spooky about these particular numerical relationships. So it goes even further than that. This is the one that just blows me away. If you take a golden proportion rectangle, so let's say roughly 5 by 8 or 0.618034 to 1, you make a nice horizontal golden rectangle there. Then you take a square out of it, and that's a square out of the left-hand side of that golden rectangle. What you're left with is then a vertical golden rectangle like that. All right, that's already pretty cool, that you can subtract a square out of a golden rectangle, and you get another golden rectangle. So let's do that again. Take that vertical golden rectangle, subtract a square out of that, and you get a horizontal golden rectangle. Okay, then you can take a square out of that and you get a vertical golden rectangle. You can take a square out of that and you get a horizontal golden rectangle. You take a square out of that and you get a vertical golden rectangle, and you keep doing that over and over and over again. And of course, then you would end up getting dimensions, if you wanted to make it like this. If you made that a square that was 3 by 3, then that would be a square that was 5 by 5. That would be a square that was 8 by 8. That would be a square that was 13 by 13. That would be a square that was 21 by 21. That one would be 34 by 34. And that one would be 55 by 55. They would be sequential Fibonacci numbers. All right, just graphically, geometrically, whoa, dude, that is so cool. But then you can take a segment of a circle, a quarter circle, and you can put that in each of those squares like that. And you get what's called a golden spiral, like this. This beautiful golden spiral. Now that golden spiral is everywhere in nature. The inside of Cape Cod in Massachusetts is a golden spiral. If you go surfing and you shoot the gap, the inside of that wave is a golden spiral. Most birds have claws and beaks that are in the shape of a golden spiral. It's everywhere in nature. But maybe the most crazy thing is a sunflower seed in nature, which actually has its seeds in 2 interlocking golden spirals, like this. So there are 2 interlocking golden spirals where the seeds are arranged. And if you take those seeds out, you'll find that the 2 interlocking golden spirals, the number of seeds are 2 sequential numbers in the Fibonacci series. So a small sunflower seed will have 21 and 34 seeds. Medium size will have 34 and 55 seeds. A large one will have 55 and 89 seeds. So in some ways, just, whoa, this is just weird how much there is in nature, how much there is in mathematics, how much there is in psychology that makes some numbers, some mathematical relationships, and some proportions maybe kind of more connected to human beings. Now, this has been used in architecture for eons. And in fact, one of the very, very oldest building complexes we know is the pyramids, the Great Pyramids at Giza in Egypt. And even way, way back with the Egyptians, some of these relationships were there. And the point of looking at the pyramids for the next few minutes is to understand how fundamentally these kinds of things have affected the making of form in architecture. So the pyramids are themselves unbelievable. They're massive. Their construction is incredibly impressive. They've been there, as you saw from that previous date. These were built 2500 BC. They were built longer before Christ than we've had time since Christ. These are ancient, ancient buildings. And their construction is incredibly sophisticated, especially for that time. They're in this completely neutral plain of the desert, and out of it rises these pure geometric shapes. How important numbers, mathematics, and geometry are for the conception of these buildings, which were this enormous building effort. And it's not just the outside of those buildings, it's deep inside how they were built. And there are numerical relationships on all kinds of surfaces and planes, even within the construction of those buildings. Now, they are, of course, equilateral triangle on all sides. And in plan, they're a square. And that square in plan is oriented to the cardinal points, north, south, east, west. So they're connected to a larger cosmos beyond that. So at a very fundamental level, they're powerful geometry that way. They're also their height in relation to a leg of the base there is in that golden proportion, about 5 to 8. So that was built in even way back then. It was built into the proportions of the making of the pyramids. Now, think of the effort that went into building these over hundreds of years. And they're made actually of massive stones. So there you can see the scale of these stones. They had to be quarried, they had to be carried to the site. We don't know exactly how they erected them. There are many ideas about this, sort of earthen ramps, but how do you get all those incredibly heavy pieces of stone stacked up and arranged in these massive pyramids? And then in addition to that, to have the kind of precision numerically that they had. On the outside of them was this very, very precise skin. And that precise skin then generated dimensions that were incredibly exacting for the kind of technology that they were using to build them. Now, in the end, we can now figure out exactly what all the dimensions of the pyramids were. And interestingly, the height of them, and we think the Egyptians used inches. Basically, it came from your finger, a digit in your finger. But the height was 5,813 inches. Of course, that's 5, 8, and 13, 3 sequential numbers in the Fibonacci series. In addition to that, if you took that 5,813 inches and you made it the radius of a circle, and then you figured the circumference of that circle, that circumference would be 36,524 inches. If you just move the decimals in that number, that's the exact days in the year, which is 365.242 days. We know the Egyptians were totally into the kind of magical quality of numbers, the spiritual nature of numbers, the magical quality of geometry. These pyramids, which basically are enormous, sort of dedicated ideas to geometry. And they were meant for a very singular purpose. They were meant to transport the pharaoh to the other world. So this is a spiritual thing they're trying to do. They're trying to commandeer the mystical nature of the world to transport this pharaoh to another life. And in order to do that, you use these very special and sacred geometries, numerical relationships, and that's what's generating the pyramids. Now, I am blown away that this architectural monument, this ensemble that's been there for 5,000 years, this ensemble that has meant so much over all that period of time, this ensemble that attracts tourists from all over the world to go and just see those phenomenal pyramids, it's all based on numbers, mathematics, and geometry. This is the fundamental message of that great piece of architecture in the pyramids in Giza. Now, that's kind of a baby step. That's the beginning of an enormous interest in architecture and numbers, mathematics, and geometry over decades and centuries and eons at this point. But let's fast forward to another brilliant mind, Leonardo da Vinci, like Fibonacci, very interested in science and mathematics and the larger world, but also very interested in architecture. And let's look at his take on some of these numbers, mathematics, geometry, proportions, and so on. So he's trying to see in the human body what proportions and geometries are special, spiritually connected to God, or to make them remarkable. So as he's doing that, he's looking at the square that is generated by the arm span versus the height. That's because your arm span is the same as your height. That generates a square. He's looking at a circle, which if you take the navel as the center and you spread the legs and the arms, you then get a circle with the navel in the center. The navel, of course, is where your umbilical cord was connected in utero, so it was the source of life before you were born. So that generates the square and the circle. And then in addition to that, there are all sorts of golden proportions that are in here as well. So the height of your body compared to the height to your navel is 0.618034 to 1, or that golden proportion. The length of your arm compared to the length to your elbow is 0.618034 to 1. The length of your leg to your knee compared to the full height of your leg, it's 0.618034 to 1. So he's finding in the human body all of these various proportions that are tied to the golden proportion. He's finding these geometries that are tied to the square and the circle. And then when he begins to think, well, how do we make architectural form for a church? And for him, it's those forms that God put in your body that should then be the spring point for this church. So it begins to be combinations of squares and circles and squares and half circles. And it begins to be then in 3 dimensions, domes and cubes. And all of those things inspire the form of the church. And then beyond that, there begin to be golden proportions that then tell you dimensions of these things in relation to each other. And that would make a more perfect, more beautiful, more spiritual, more God-connected building. Now, that begins to be the actual genesis of the centrally planned church in the Renaissance, a very fundamental innovation of Renaissance architecture. But again, rooted very much in numbers, mathematics, and geometry. So next time we'll be looking at other manifestations of this, all through the history of architecture, but certainly it's impossible to understand form making in architecture without understanding how fundamental numbers, mathematics, and geometry have been.